The second speaker today is Dr. Hyun-Jong Jung. He did his PhD in chemical engineering under the direction of Professor Venice. From 1980 to 1985, he worked for American Dynamite in the area of petroleum refining catalyst development. From 1985 to 88, Dr. Jung worked for Johnson Matthey as new product development manager of environmental catalyst development. Since 1988, he is with Yugong Limited, Korea. Currently, he is director of Ulsan Research Center. Also, he is known as senior member of Professor Venice's Korean Mafia, I guess. His title is de-oxidation catalyst for tough air pollution control problem.
To be a good karaoke singer in Korea, you got to choose a good microphone. It seems that I'm the only one representing industrial research among Korean speakers. So I'd like to tell that I'm working with a company called Yugong. Let me test this.
Press the but this yeah, okay.
Company called Yugong, which is the largest petroleum and petrochemical company in Korea. Its size and sales is pretty close to Philips in the United States. To start my talk regarding new oxidation catalyst for air pollution control, I'd like to show the current management issues in major oil companies. As you can see here, most of the top priority subjects are technical and catalysis related, such as Clean Air Act and heavy oil upgrading. Next. Well, the greatest success story in the field of environmental catalysis, at least in a commercial sense, is, in my opinion, automobile three-way catalytic converter. The technology is really well established, and the benefits from this technology, I think, is in the process of being carried over to a new area, which is the control of emissions from stationary sources such as industrial boiler. Well, I often hear that there are not much to do in this environmental oxidation catalysis area because so many people have studied so many possibilities for too many years. Well, but because our desire to have a clean environment never stops, the kind of pollution control requirements is becoming increasingly restricted, creating new R&D needs for better and improved catalysts. I'll give you some examples. Cold start emission control catalyst. More than 50% of carbon monoxide and non-methane hydrocarbons are emitted during the first 100 seconds after the cold start of a vehicle. Also, they ask for 100,000 miles durability compared to current 50,000 miles. Also, after treatment devices for diesel trucks and buses are being asked. I thought that the cold start emission control catalyst is basically the catalyst activity problem. 100,000 miles durability is the catalyst longevity problem. And the diesel after treatment device is the catalyst selectivity problem because for the diesel exhaust control, you want highly active catalyst for carbon monoxide hydrocarbon oxidation and soot ignition, but you want low activity for SO2 oxidation, prevent downstream formation of sulfates. So this is very challenging for catalyst R&D people dealing with catalyst activity, selectivity, and durability. Also, I thought that the diesel exhaust control problem, especially diesel particulate removal, is the most difficult problem to be solved by using oxidation catalyst. And if you have a nice system for this, you can readily solve the other cold start emission of durability problems. At least that will greatly help. And there's another reason that I'm particularly interested in diesel exhaust control as a Korean. As you can see here, the portion of diesel vehicles in Korea is unusually high, 40% compared to 3% for United States and 13% for Japan. Next slide, please. This shows the composition of diesel particulate. You can tell easily that most of the majority portion of these diesel particulates are combustible, except this, sulfate. So you can reduce the sulfate particulates by either reducing the sulfur content in the diesel fuel or by making the catalyst very selective. And you need a high activity catalyst to combust this. For this unburned oil or unburned fuel, we call this soluble organic fraction. You can use typical flow-through type oxidation catalyst if the catalyst is good. But for this carbon, it's somewhat tougher. Next. So the kind of technology which has been developed thus far is the using some kind of a filter, and the particulates are trapped. And these particulates should be removed by some means. People have been using diesel burner, electric heater, but those are very complex and very hard to control, and also very expensive. So if you can remove these trapped particulates by using catalysis, they will be safe and cost-effective, and they will be a very nice system. Next slide, please. Well, for this diesel exhaust control catalyst, they have been just adopting the old oxidation automotive catalyst technology. Aqueous impregnation, platinum and/or palladium on alumina support. Lately, they are using titanium. They are trying titanium too. But here, for some reason, I don't know, but because this is maybe cost-effective, we have been using aqueous impregnation, I think, for too long years. Next. We have some problems in the current technology for diesel exhaust control. Platinum is very active, but not suitable for diesel exhaust control because of excessive activity for SO2 oxidation. Well, a few years ago, Johnson Matthey, who is one of environmental catalyst leaders worldwide, they reported that platinum rhodium may be a good catalyst for diesel exhaust control because rhodium can decrease the activity for SO2 oxidation, but that rhodium addition also decreases the activity for CO and hydrocarbon oxidation. So I joked that rhodium may be a too expensive deactivator for platinum. Lately, those industries reporting that vanadium can be a kind of selectivity promoter. That's where they stand. Also, some companies are trying palladium. When you use palladium on titanium, actually the activity of platinum increases. But that activity still is not enough to make diesel exhaust control system practicable. Palladium is nice simply because that is not active for SO2 oxidation. But we need some activity improvement if we want to use palladium. Okay, next slide, please. Don't pay any attention to this part because this tells some kind of unusual, stupid, my philosophy about the catalyst business. But this, I'm talking about this conventional preparation of colloidal catalyst. If you look over the patent literature very carefully, you can find precious metal colloidal coatings even in the patents in 1960s, 1968, 69. They are starting from metal salt. They are making some kind of a very fine particles of metal hydroxide and redisperse in a solution and reduce that in a solution using some kind of reductant like formaldehyde. Then you get the colloidal metals. Next slide, please. This conventional type of colloidal technology is really a complex, very involved, and not easy to control. Usually, when you use the kind of hydroxide precipitation and redispersion and the reduction technology, you get a very large particle size and very unstable. And also, the preparation process, there's some toxicity involved. Also, I already told you that the process involved, it takes 3 days, usually, if your technician is skilled. We, about 2 years ago, we started kind of extensive research, more like to look at this colloidal preparation chemistry from totally different viewpoint. Only thing I can tell is the concept is utilizing the technology widely used in homogeneous catalysis to heterogeneous catalysis. So somewhat different chemical route which can be prepared in one step. This is the characterization data for the initial sample, which was actually obtained about 2 years ago. So now we can control better, but the particle size is less than 100 angstrom, and particle size distribution is controllable, and stability is very good. Okay? And we are not using a toxic aldehyde type of reductant, and preparation can be finished in 6 to 4 hours. Next slide. Well, this is a typical microreactor that you prepare a lot of samples to find any unusual catalyst samples for lab. Okay, this one shows the CO conversion data for alumina-supported precious metal catalyst. These 2 samples tells the aqueous, conventional type aqueous catalyst. As well, reported in the literature, palladium catalyst shows very low CO conversion activity. It's about 50% at 200 degrees centigrade. Platinum is more active catalyst than palladium, so about 150 degrees centigrade, it reaches 100% conversion. Oh, by the way, all the metal loadings, here is a 0.2 weight percent, and this conversion was obtained at the gas hourly space velocity of 60,000 whisker per hour, and all the reactants here are 500 ppm, and the balance is air. Next. This more like substantial activity improvement using this pre-treated catalyst colloids was also observed for the hydrocarbon oxidation reaction for this ethylene conversion compared to the conventional aqueous type. Our colloidal catalyst shows the improvement, and the improvement was same for platinum. Next. We tried this same technology for titanium support, and this conventional aqueous type compared to alumina also showed activity improved when you use titanium support. But when we use our special impregnated solution, the conversion is almost 100% in the temperature between room temperature to 45 degrees centigrade. So we think this catalyst can have a good potential for the application at low temperatures, like cold start automotive emission control, or the indoor air purification, or refrigerator odor removal. Next. But the highlight of this, new catalyst impregnation technology comes from this. When we measure the SO2 conversion, that platinum catalyst shows a higher SO2 conversion compared to the aqueous impregnation platinum. But for the palladium, despite of unusually high activity for CO and hydrocarbon oxidation for this palladium catalyst, this special palladium catalyst shows a very low SO2 conversion in the temperature range between 400 to 600 degrees centigrade. This is kind of the range that the catalyst will be exposed in the diesel emission control in the real vehicle. Next slide, please. So we utilize this new impregnation solution technology. We developed wash coating technologies for all different type of filter materials, which have been developed worldwide. Honing, ceramic honeycomb filter, and metallic foam, ceramic fiber filter. There are some, on a relative basis, this may be better than this for some aspect, but anyhow, for our study, we have been using this ceramic honeycomb filter for the major portion of our study. Next slide, please. For the process development, this engine test equipment is like a pilot plant. So this is the engine dynamometer that we use for testing the catalyst in the real diesel engine condition. And the catalyst is here. This is control unit. Next slide. If you run the engine at the temperatures where the soot ignition doesn't occur, the back pressure increases because the soot is trapped in the filter. But because there's some soot oxidation or hydrocarbon CO oxidation is occurring, the rate of back pressure increase differs depending on the catalyst. So this shows the back pressure increase for no catalyst. Conventional aqueous type palladium, there's some relief in the back pressure increase. Platinum, this is conventional aqueous type, pretty good. But our palladium catalyst is actually better performance than platinum in the engine test. Platinum colloid, the new technology, performs best, but platinum has a selectivity problem. Next. Okay, and then you increase engine exhaust temperature. Then at a certain temperature, the pressure suddenly drops down because all the soot collected there starts to burn. We call it the balance temperature or regeneration temperature. Okay? Low catalyst, the soot starts to burn at around 570 degrees centigrade. With a platinum colloid, we have 270 degrees centigrade regeneration temperature. Platinum chloride, 350. Palladium colloid is our new technology, 340 degrees centigrade. Conventional aqueous type palladium, 400 degrees centigrade. The range of diesel exhaust gas temperature range from 100 to 400 degrees centigrade usually. So to make this catalyst to be practically usable in the real condition, the temperature should be around 300 degrees centigrade. Next. Another one, we analyze the exhaust gas for the SOx, for the SO3 and SO2. Low catalyst, there are about 12% SO3 and 88% SO2. As the catalyst goes through this platinum catalyst, there's oxidation occur and SO3 composition increased significantly. Platinum chloride 40%. Platinum colloid not much increase. Aqueous type palladium is a selective catalyst there. So this engine test shows very good agreement with the microreactor test results. So we now extend this catalyst to the real vehicle. This is the bus that we used for the real vehicle test. Next slide, please. Yeah, this is the very initial design we made for the bus. Well, you can put more filters if you want to get a better durability or longer use. But that is also relation to cost. Anyhow, this is a kind of a model that you can see, and this is the real stuff. Initially, we just have an intention to utilize this diesel particulate trap, kind of replacing the muffler. So because that's the more like a sound absorber, it works almost better or same as a muffler. So initially, we didn't put any insulation. Next. There's the insulation. Later, we put the insulation to maintain high temperature. Instrument. Next. Okay, this is I don't think even in the United States or in Europe they are using this technology. We put a special smoke test in the car. It's more like in situ performance test equipment. Next. So this shows the difference. Next. This can be used for the these heavy duty trucks too. Next. Okay, without the trap and with trap. Next. Because of time, I have to omit all field test results. But so far, we have finished 10,000 kilometer testing. We run highway to intentionally deactivate the catalyst thermally. The highway mode, you have problems to burn the particular with this catalyst because the exhaust temperature is very high, 500, 600 degrees centigrade. Usually the performance of the catalyst is measured here by the back pressure. Our initial catalyst, initial trap system shows the about 10 millimeter Hg back pressure increase compared to the nothing equipped there. After 10,000 kilometer, the back pressure increased to now about 80 milli Hg. Usually 200 milli Hg back pressure is considered to be kind of a commercial limit, which gives about 5% fuel penalty. I used to speak pretty English, but seems like my English is frozen. So I really couldn't, show you all the slides that I wanted to show you. But I think, we take a very unconventional concept for catalyst preparation and come up with very interesting results. Now we are preparing to do very organized and well-defined research to find whys as well as to improve our hows. Thank you very much for your attention.
Thank you, Dr. Zhou. Now floor is open for.
Borrow your microphone. You've shown us some very impressive results for these colloidal suspensions as precursors to catalysts. I have some difficulty understanding, though, why does the higher activity arise? From what I know about palladium catalysis for CO oxidation, this is a structure-insensitive reaction, all the way from very small particles to single crystals. The colloidal particles are in the 50 to 100 angstrom range, as you show on one of your slides, so they're fairly big. So what is the distinguishing feature when you put this on alumina or titanium? And can you also tell us whether, when you compare catalysts by conventional preparation from the chloride, whether we talk about the same weight loading, the same surface area, or what is the same? In other words, what's the basis of comparison? Because that's critical to understanding how these catalysts perform.
Actually, yesterday, listening to all the talks here, I start to regret that I asked for coming here and to give this presentation because the most of the things still here is I wanted to explain why. But for me, I haven't really done too much to tell the reasons why these catalysts behave this way. But in some of the slides that I omitted, when I started to utilize this concept for my development objective, I really cannot explain that scientifically, but from my experience, very empirical, working in the environment oxidation catalyst. When you put in a very low metal loading, precious metal loadings, palladium or platinum, the catalyst activity is awfully low, very awfully low. So I had a kind of some feeling that there may be some kind of strong metal support interaction involved, at very low metal loadings, and that has a kind of monolith type of, there. And maybe activity would be higher when, metal is, fully reduced phase. And maybe at very low metal loadings, the palladium, especially palladium, may not go to that fully reduced metal-like structure. That was my hypothesis that I made even before working this. But measuring chemisorption, measuring surface area, measuring metal distribution in the catalyst support, because these colloidal catalysts are somewhat bigger, big particles, so that catalyst would not distribute all through the micropores. So those things we plan to investigate those whys, but I have to tell you that in industry, I hate to tell that, for the very time limiting objective and time target, once you go for final product and you refine the system later.
But is the metal loading the same?
Yeah, the metal loading, all this, actually we have maybe thousands activity testing results. I only showed you some highlights for this talk, but the metal loading that I showed on this slide is 0.28%.
I think you just said that you have not yet had time to do the chemisorption measurements to see if there are differences which would be applied to what Alex was talking about. But I'm curious, with your colloidal technique, how small can you go in particle diameters? You showed here 50 to 100.
Mm-hmm.
Does the technique have potential of providing particles well below 50, perhaps in the 10 to 30 angstrom range?
We have solution which has about 30 angstrom particles. I mean, that colloidal chemistry, I hope that I have some chance to go over details of that colloidal chemistry, but there's a lot of variables. So let's say, let me reveal this. We are using some kind of dispersant in the solution, and with the dispersant, with varying the metal concentration, we can go down to smaller particles.
Maybe we can take one more question.
One of the impressive slides you had was a very low temperature of operation in some of your systems, namely room temperature at 50 degrees centigrade. So two questions. One is, do you visualize this as a potential solution to the light-off problem in the automobile gasoline catalysis, where we're looking at the electric to heating catalysts?
We're working on that. I hope so.
And secondly, probably don't know the answer for, like me, an industrialist, we go on to other things, but this phenomena, I would imagine, is not a particle size phenomenon, but to lower the operating temperature by such amount is spectacular. Do you have any explanation for it?
Well, I hope that I can come up with the answer for the question for the next Seattle AICH meeting, because I have a plan to present. At this time, we are conducting characterizing studies because this behavior we are observing is really unusual. But one thing, Alex, mentioned that he cannot understand why the catalyst shows high activities by using colloidal. But in the real industry, I wouldn't label the company, but in the real industry, for the very troublesome customers who wants real high activity, this old conventional colloidal type catalyst has been utilized for their satisfaction. So the light-off, you can obtain low temperature light-off using this colloidal catalyst. But the conventional technology can make only colloidal with platinum. They have never been successful with other metals. So that's the kind of another breakthrough that I think I can provide. We are working on for other metals. Also another thing, for the hydrotreating catalysis, I think I can provide some unusual behavior there, because we are getting molybdenum cobalt oxide. When that is provided to refinery, we are sulfiding the catalyst, but all the research people say that the common phase is active phase. Then I can, as a refinery guy, I can ask that why don't you provide me more, catalyst in the most active phase form? So